Hello and welcome to video lesson 7 on plastic behavior. For this session, you should read Beer and Johnston section 212. Our learning objectives are to define linear elasticity, plasticity, and permanent deformation, to explain the response of linearly elastic materials to applied loadings, to explain the response of linearly elastic, perfectly plastic materials, and finally, to state the conditions under which the results derived in the remainder of this course are going to be valid. So let's talk about the loading response of typical materials to greater than yield stress. Now, for the curve that I've shown here, we've got a linear elastic region. However, there are some materials that are non-linearly elastic, especially in the biological um, and life sciences area that can hold a lot of high strains. However, for most materials that we're working with, we're going to be dealing with linear elasticity. And this curve is going to be a straight line in the linear elastic region. However, we're going to note that the material will start to yield, but it may gain in stress over the plastic region. Once we get to larger deformations, we're going to have what we call plastic deformations. And once we get into the plastic range, the material is going to be deformed permanently. So let's take a look at what deformations might look like. So if we apply deformations to a structure by loading it up, we might apply deformations that are going to result in less than the yield stress at some point in the structure. And at that point, we would have stresses and strains that might follow this red trajectory. However, if I exceeded the proportional limit and the yield stress, I would move into the plastic region and I would continue to follow along the stress strain curve and I would sweep out this green trajectory. Then if I stopped loading, my material would return back along a line that's sloped at the modulus of elasticity, and we would come back and hit the epsilon axis, the strain axis. And then we would have some permanent strain in the material. We would have some permanent deformation that occurs as a result of this loading trajectory. Then if we started over, we would start from a new length and we would have essentially linear elastic behavior again for most metals until we hit the stress strain curve for what we would call the virgin material. So if we hit the stress strain curve here and continue to exceed the yield stress, we would come to a new point on the stress strain curve. And then if we took the loading off, we would come back along the line and we'd be at a new point. We would have more permanent deformation. And then if we did this yet again, we would continue to move further out along the stress strain curve in a similar fashion. And if we did this a number of times, what we would have done is we would have strain hardened the material. And in the manufacture of many civil engineering products like reinforced concrete pipe, it's a common practice to take the reinforcing wire that is going to form the cage around which the concrete is placed. And you would start with wire that is about 10 KSI yield strength, and you would go through a drawing process where you would strain the material to very high strains. And by the end of that drawing process, you might come out with a yield stress of somewhere around 70 KSI. So you would get a higher yield stress in materials by going through this drawing process and subjecting the materials to some permanent deformation and some strain hardening. So let's talk briefly about linearly elastic, perfectly plastic materials. You might need to know something about this in reinforced concrete. So for linearly elastic, perfectly plastic behavior, we've got one part that is linearly elastic, where the stress strain curve is going to be linear. The slope of the stress strain curve is the modulus of elasticity. And then in the perfectly plastic region, the stress strain curve is perfectly flat. So as we continue to deform a bar, beyond the yield stress, it will carry the same loading and it will just continue to deform and deform and deform and deform until it snaps eventually. However, it's going to take a lot of deformation for most metals compared to the yield stress to cause this to happen, and it's a very flat line. So in many building codes like ACI 318, we would have assumptions, the assumption of perfect plasticity once we've exceeded the yield stress. So we would have essentially a flat curve here. So by plasticity, we mean the behavior of the constitutive behavior of the material beyond the yield point. In other words, the stress-strain relationships beyond the yield point. Now, for a perfectly plastic material, the stress would stay constant as we exceed the yield strain. So for this course, we're only interested in a subset of these behaviors that we've talked about so far. So for problems in this course, we're going to consider linearly elastic materials only. So materials that would follow trajectories like the red one on this stress strain curve. We will not be stressing materials past the yield point. If we stressed materials past the yield point, in some cases, the assumptions about the displaced configuration would no longer be valid. The constitutive laws would no longer be valid, and therefore the results would be no longer be valid. So we are requiring linear elastic behavior for all the results that we're going to derive for the remainder of this course. And that's the end of video lesson 7.